In this video, we're going to be introduced to atomic and subatomic terminology along with various notations used for elements. In order for us to talk about atomic terminology, we first have to define what an atom is. An atom is the smallest unit of ordinary matter and is the basic unit for an element. Well, what is an element? An element is a substance that cannot be broken up into two or more simpler substances by any means. In other words, an element is a substance composed of only one type of atom. An example of an element would be iron or bromine. The next term we'll talk about is a molecule. A molecule is defined as two or more atoms of the same element chemically bound together. An example would be oxygen gas and nitrogen gas. The last term we'll talk about is a compound. A compound is defined as two or more atoms of different elements that are chemically bound together. For example, table salt, or also known as sodium chloride, magnesium chloride, and potassium fluoride are all considered compounds. Note, nitrogen gas, hydrogen gas, and oxygen gas are not compounds. Instead, they fall under the definition of a molecule. So I have a question for you. Is water an element? If you said no, you are correct, because water is made of hydrogen and oxygen, and this falls under the definition of a compound. Now, let's dive in and talk about what makes up an atom. An atom has three subatomic particles: protons, neutrons, and electrons. Protons and neutrons are found in the center of an atom, which is called the nucleus, while electrons are found surrounding the nucleus. Some properties of these subatomic particles are that protons have a charge of +1 and a mass of 1.673 times 10 to the power of negative 27 kilograms. Neutrons have a charge of 0 and have a mass of 1.675 times 10 to the power of negative 27 kilograms. And last, electrons. They have a charge of -1 and a mass of 9.109 times 10 to the power of negative 31 kilograms. Now that we have familiarized ourselves with these concepts, let's look at how these subatomic particles are organized by looking at a Bohr diagram of lithium. So here's a Bohr model of lithium. The first thing you can identify is the nucleus, since that's the center of the atom. The next thing you may have noticed is that these electrons are part of this ring-shaped structure. These ring-shaped structures are called electron shells. The innermost ring is the first electron shell, and we'll call this n equals 1, and it can hold a maximum of 2 electrons. Each of these shells can hold a maximum number of electrons that can be expressed with the formula 2n to the power of 2. Using this formula, we can see that the second and third ring can hold 8 and 18 electrons respectively. An important rule to mention is that electrons are filled from the innermost to outermost shell. Once that respective shell has reached its maximum capacity, the electrons are added to the next outermost ring. The last thing we need to discuss is valence electrons. Valence electrons are the electrons found in the outermost shell. So we can see that in lithium's outermost shell, which is the second ring, it has 1 electron. So we will say that lithium has 1 valence electron. I know this was a lot of information, but we're going to go through some practice problems to help clarify any confusion. So in this example, we're given a Bohr model of boron. What we don't have is electrons filled out. But it tells us that boron has 5 electrons. And what we're supposed to do is find how many valence electrons does it have and which cell are these valence electrons located at. So based off the formula, that we were given in the last slide, we know that the maximum number of electrons that can be in any shell can be expressed as 2n to the power of 2. So the first shell can have a maximum of 2 electrons. So let's fill in those 2 electrons. Now we have 3 electrons left, and we know that the second ring can hold a maximum of 8 electrons. So it means in the second ring, we're going to have 3 electrons. So what that tells us is that boron has 3 valence electrons. In the next video, we'll talk about concepts that will help us solve these type of problems much faster. And we'll also talk more in detail about how these electrons are spaced around the nucleus when we get to electron configuration. Until then, let's talk about our last concept for the video, which is notations. The 2 primary ways elements are denoted are the periodic table notation, which is probably the one you may be more familiar with, and nuclear notation. The periodic table notation provides us with 2 important properties about an element: the atomic number and the average atomic mass. The reason we call it an average will be discussed in a future video. With nuclear notation, the top number, which is denoted as m, represents the element's mass number. The bottom number, denoted as A, represents the element's atomic number, and this X represents the element's symbol. So if I give you the periodic table notation or nuclear notation of an element, you should be able to convert it to the other notation. For instance, let's convert the periodic table notation of carbon to its nuclear notation. We know that in nuclear notation, the top number will represent the mass number, and the bottom number will represent the atomic number. With that, we can simply plug in these numbers in the correct spot to give us our nuclear notation. Sometimes people may round the mass to the nearest whole number. So you may see carbon written like this. When given a nuclear notation of an element, people forget which number corresponds to the atomic number and the mass number. So in an informal way, people remember which is the atomic and mass number is that the mass number will always be greater than the atomic number. So if that helps, then perfect. With that, thank you for watching this video, and I hope to see you next time.